Regulating body temperature is a vital biological function for all living creatures. But for giant dinosaurs, this task presented a particularly formidable challenge. When we think of dinosaurs like the massive sauropods, reaching lengths of over 100 feet and weighing as much as 70 tons, it's hard to imagine how their enormous bodies managed to maintain a stable internal temperature. Larger animals face greater difficulties in both shedding excess heat and retaining it when needed due to their volume to surface area ratio. Essentially, as an animal increases in size, its volume, which generates heat, grows faster than its surface area, which loses heat, making temperature regulation a complex process. In modern animals like elephants and whales, this issue is apparent. These creatures have evolved various physical and behavioral adaptations to ensure their core temperature remains stable. For example, elephants have large ears with numerous blood vessels, allowing them to dissipate heat efficiently. Similarly, whales maintain stable body temperatures by having a thick layer of blubber to insulate themselves in cold waters. However, for dinosaurs that roamed prehistoric Earth, adapting to temperature changes may not have been as straightforward. The climate during the Mesozoic era, which spanned hundreds of millions of years, was not consistent. It varied from lush, humid environments to periods of intense aridity and even temperature fluctuations. Dinosaurs faced these climatic challenges while dealing with their massive size. The idea of how these ancient giants managed to survive in such varied conditions is one of the most fascinating questions in paleobiology. Did these dinosaurs function more like reptiles, which are ectothermic, relying on external sources of heat, or did they adopt some endothermic, internally generated heat traits similar to mammals and birds? Modern reptiles rely heavily on their surroundings to regulate their temperature, which allows them to thrive in warm environments, but also limits their size and activity levels in cooler climates. Dinosaurs, however, thrived in nearly every part of the world, from the icy poles to tropical forests. This suggests that their temperature regulation strategies were more complex than those of modern reptiles. Some paleontologists have theorized that these giant dinosaurs may have possessed metabolic adaptations, allowing them to generate and maintain heat internally, despite lacking the typical features of warm-blooded animals. The question of whether these dinosaurs were warm-blooded or cold-blooded remains open to debate, but understanding the relationship between body size and temperature control helps to shed light on how they may have lived. One prominent theory that has emerged to explain how giant dinosaurs regulated their temperature is known as gigantothermy. This concept suggests that due to their enormous size, dinosaurs were able to maintain stable internal temperatures passively. The term gigantothermy is often associated with leatherback sea turtles, which use their large size to retain heat in their bodies despite being cold-blooded. This principle might have applied to large dinosaurs as well. By virtue of their size, these creatures would have been slow to absorb heat and equally slow to lose it, creating a kind of self-regulating system that helped maintain a relatively stable body temperature. For instance, consider a massive sauropod with its immense bulk acting as an insulator. During the heat of the day, a giant sauropod would have absorbed heat gradually due to its large size, while at night, it would have retained that heat effectively, reducing the likelihood of drastic internal temperature drops. This phenomenon could mean that these dinosaurs were able to keep their body temperature relatively constant over a 24-hour period, regardless of external environmental changes. Interestingly, gigantothermy doesn't imply that these dinosaurs were endothermic in the same way mammals are, which generate heat internally through high metabolic rates. Instead, it suggests that their thermal regulation relied more on their size and physiological adaptations rather than a fast metabolism. Fossil evidence supports this idea, showing that the bones of some large dinosaurs have growth rings similar to modern reptiles, indicating that their metabolism might not have been as high as traditionally warm-blooded animals. Yet, their sheer size could have allowed them to maintain relatively high internal temperatures through passive thermoregulation. Some scientists propose that large dinosaurs like sauropods might have used other means in conjunction with gigantothermy to regulate their body temperatures. For example, their long necks and tails could have functioned as thermal regulators, helping to distribute or dissipate heat more efficiently. The extensive vascular systems found in sauropod vertebrae might suggest that blood circulation through these areas played a role in managing temperature fluctuations, functioning like giant radiators. This combination of passive temperature regulation through size and possible vascular adaptations indicates a sophisticated balance between physical traits and metabolic processes. Overall, the idea of gigantothermy offers a compelling explanation for how large dinosaurs may have coped with the challenges of thermoregulation. While it might not provide the entire picture, it highlights the significance of size in determining how these prehistoric giants managed their body heat. This insight not only illuminates how they lived and thrived, but also offers a fascinating glimpse into the unique evolutionary solutions that nature devised for these colossal creatures. The physical characteristics of giant dinosaurs weren't just impressive in size. They were likely instrumental in helping these creatures regulate their body temperature. When studying the fossilized remains of dinosaurs, paleontologists have uncovered clues that suggest many of these physical features weren't just for show. They may have played a crucial role in thermoregulation. By looking closely at the anatomy of these prehistoric giants, researchers have begun to piece together how these physical adaptations could have functioned as natural air conditioning systems or heat retainers. One of the most obvious adaptations that could aid in temperature regulation is the elongated necks and tails of sauropods. These massive dinosaurs, like Diplodocus or Brachiosaurus possessed extremely long necks which could stretch up to 30 feet or more. While these necks were likely advantageous for reaching tall vegetation, there's evidence to suggest that they also served another purpose: dissipating heat. The long extended surface area of the neck could have acted as a radiator, allowing excess heat to be shed more efficiently. Blood vessels running through the neck and tail would transport warm blood away from the body's core, cooling it down as it passed through the surface of the neck or tail before returning to the core at a lower temperature. This circulation system would create a cooling effect, much like how elephants use their large ears to dissipate heat. Furthermore, studies on the vertebrae of sauropods reveal an intricate network of air sacs, similar to the respiratory system found in modern birds. These air sacs are part of a system known as the avian-style respiratory system, which is not only highly efficient for breathing, but may also serve a thermoregulatory function. This respiratory system creates a continuous flow of air through the lungs, enhancing oxygen exchange and preventing the buildup of excess heat. By having air sacs spread throughout their bodies, including in their vertebrae, sauropods could have maintained a steady internal temperature, especially considering their massive size. This discovery adds to the theory that these dinosaurs had evolved not only for efficient breathing, but also for managing their body temperature more effectively than traditional reptiles. Theropod dinosaurs, like the mighty Tyrannosaurus rex exhibited their own unique physical traits that likely helped regulate their temperature. While they were not as large as sauropods, these creatures faced similar challenges in managing body heat due to their substantial size and active lifestyle. Studies have shown that some large theropods had highly vascularized skulls. This dense network of blood vessels, visible as impressions on fossilized bones, indicates that blood flow through the skull could help to cool the head, similar to how crocodiles regulate their temperature today. Crocodiles used the blood vessels in their heads to release heat, and it's plausible that theropods employed a similar strategy. When these dinosaurs faced intense heat, increased blood flow through their skulls could have allowed excess heat to be released, preventing overheating. Another physical feature that has captured the interest of paleontologists is the presence of crests, plates, and frills in various dinosaur species. Stegosaurus, for example, is famous for the double row of large, flat plates running along its back. While these plates have been debated for years as a defense mechanism or display feature, recent research suggests they may have played a significant role in thermoregulation. Stegosaurus plates contained numerous blood vessels, hinting that they could have been used as thermal radiators. By pumping blood into these plates, the dinosaur could have allowed heat to escape or, conversely, could have absorbed heat from the environment in cooler conditions. This dual functionality would provide a flexible means of maintaining stable internal temperatures. Ceratopsians, like Triceratops asterisk, had large frills extending from their heads. These frills, although often considered primarily for display or protection, could also have served a thermoregulatory purpose. Similar to Stegosaurus plates, the frills had blood vessels running through them, which may have helped regulate temperature. In addition, paleontologists have speculated that frills could have acted like sails, capturing cool breezes to help dissipate body heat. This multifunctional feature indicates that these dinosaurs might have had sophisticated adaptations to cope with temperature changes in their environment. Some dinosaurs also exhibited features like feathers, which were initially assumed to be purely for insulation. However, the discovery of feathered theropods like Velociraptor asterisk, and Uteranus asterisk shows that feathers could have had multiple thermoregulatory functions. Smaller dinosaurs may have used feathers to retain heat in colder conditions, similar to how birds use them today. For larger dinosaurs, feather-like structures could have served a dual purpose of insulation and aiding in heat dissipation through specialized patterns of blood vessels. These feathers might not have been as dense as those of modern birds, suggesting a more complex role in temperature control. Additionally, scientists have studied the skin impressions of some dinosaur fossils, which indicate that certain species may have had a range of scales, osteoderms, bony deposits within the skin, and even primitive sweat glands. Some researchers believe that dinosaurs like the heavily armored Ankylosaurus asterisk used their bony armor plates not just for defense, but also as a way to regulate their internal temperature. These plates could have had blood flow running through them, allowing heat to be released or absorbed as needed, much like the plates of Stegosaurus. Such findings point to the idea that thermoregulation in dinosaurs was not just a matter of size, but also a combination of physical structures and internal physiology. Moreover, the discovery of large blood vessels in the bones of many large dinosaurs suggests that they had the capacity for enhanced blood flow. This would have been essential for transporting heat throughout their massive bodies. The bones of some dinosaurs reveal channels for large blood vessels, indicating that these animals could direct blood flow to specific areas when cooling or heating was necessary. For example, blood flow could be increased to the limbs or to the surface of the skin during hot weather, allowing heat to escape more efficiently. During cooler periods, the blood flow could be reduced to these areas, helping to conserve body heat. In conclusion, the physical adaptations of giant dinosaurs suggest that they evolved in ways that enabled them to regulate their body temperatures despite their massive size and the diverse environments they inhabited. From long necks and tails to vascularized skulls and specialized respiratory systems, these adaptations paint a picture of dinosaurs as highly sophisticated creatures with a range of strategies for managing temperature. By understanding these physical traits, we gain not only a deeper appreciation for these ancient giants, but also insight into how life on Earth has adapted in the face of environmental challenges over millions of years. In addition to physical adaptations, giant dinosaurs likely relied on a range of behavioral strategies to regulate their body temperature. While fossils provide us with clues about their physical attributes, understanding their behavior requires a bit more detective work. However, by observing the behaviors of modern animals and combining that with fossil evidence, scientists have begun to piece together how these prehistoric giants might have used their environment and instincts to stay cool or warm. One possible strategy was the use of their environment to either gain or lose heat. Many modern reptiles, such as crocodiles and lizards, are experts at behavioral thermoregulation, and it's likely that dinosaurs used similar techniques. Basking in the sun, for instance, is a behavior we see in cold-blooded animals today, allowing them to absorb heat directly from the sun. For large dinosaurs, especially those that lived in cooler climates or experienced cooler mornings, basking in the early sun could have been a way to raise their body temperature after a cold night. The large surface areas of their bodies, whether it be the broad, flat plates of Stegosaurus*, or the massive bodies of sauropods, would have allowed them to soak up warmth quickly from the sun's rays. Likewise, these dinosaurs might have sought shade during the hottest parts of the day, especially in hotter tropical climates. For instance, under the canopy of large prehistoric forests, giant herbivores like Diplodocus*, may have spent time cooling off to avoid overheating under the intense sun. These behavioral patterns would have been essential for managing the heat load on their bodies, especially considering how much time large herbivores spent grazing in open areas. Like modern-day elephants, which often seek shade or mud baths during the hottest times of the day, dinosaurs would have employed similar methods to ensure they didn't overheat. Water would have played an important role in the lives of these giant creatures as well. For many animals today, from hippos to crocodiles, water is not just a source of hydration, but also a valuable tool for cooling off. Dinosaurs living near rivers, lakes, or swampy regions may have taken advantage of these water sources in similar ways. Wading into water or even submerging themselves could have helped them cool down, especially during the hot Mesozoic summers. The vast surface area of their bodies would allow for efficient heat loss when submerged, making water an excellent tool for temperature regulation. Some paleontologists have even suggested that the elongated tails of sauropods might have helped them balance or move through water, though more research is needed to confirm this theory. Beyond water, large dinosaurs might have used mud and dust as cooling agents. Modern elephants often roll in mud to cool their bodies and protect their skin from the sun. Similarly, dinosaurs may have engaged in such behaviors, particularly species that lived in environments with limited water sources. Coating themselves with mud would not only have provided cooling relief, but also served as protection from the sun's direct rays, creating a layer of insulation that slowed down the absorption of heat. In addition to its cooling properties, the mud could have acted as a deterrent for parasites or other skin irritants, another reason why this behavior would have been advantageous. Dinosaurs may have also altered their activity patterns to avoid extreme temperatures. Many animals today, particularly those living in hot climates, are most active during the cooler parts of the day, such as early morning or late evening, and spend the midday hours resting or seeking shade. This strategy of avoiding activity during peak heat could have been essential for large dinosaurs, especially those living in regions with intense sunlight. Sauropods and large theropods, due to their enormous body mass, would have been prone to overheating if they exerted too much energy during the hottest parts of the day. By focusing their feeding or hunting activities during cooler hours, they could avoid the risk of heat stress. Additionally, some dinosaurs may have migrated seasonally to take advantage of cooler climates. Migration is a behavior seen in many modern species, such as wildebeest and caribou, which move to more favorable environments depending on the time of year. While the fossil record provides only limited evidence of dinosaur migration, it's plausible that certain species, especially those in regions prone to seasonal changes, moved between habitats to avoid extreme temperatures. Large herbivores in particular would have had the physical capacity to travel long distances in search of food and favorable climates, much like modern herbivorous mammals. The nesting behaviours of dinosaurs may have also played a role in thermoregulation, particularly for smaller species or juvenile dinosaurs. Fossil evidence shows that some species, like Maiasaura*, built nests for their young, suggesting they may have taken special care to ensure a stable and safe environment for their eggs and hatchlings. These nesting areas could have been strategically located in places where temperatures were more moderate, such as shaded forests or near water sources. By choosing environments that offered natural climate control, dinosaurs could have ensured that their offspring weren't exposed to extremes of heat or cold, giving them a better chance of survival. Juvenile dinosaurs, being smaller and more vulnerable to temperature changes, might have relied on their parents' or group behaviour to help regulate their body temperatures. There is some evidence to suggest that certain species may have engaged in communal nesting or herding behaviours, allowing individuals to huddle together for warmth during cooler periods or to share shaded areas in hotter climates. This type of social behaviour, seen in many modern animals, would have provided an additional layer of protection against extreme temperatures and allowed young or more vulnerable dinosaurs to thrive in challenging environments. Another intriguing possibility is that some dinosaurs may have evolved complex social behaviours related to thermoregulation. Herding, for example, might not only have provided protection against predators, but also offered thermal benefits. By clustering together, dinosaurs could have created microenvironments that were cooler or warmer depending on the circumstances. During cooler nights, for instance, large groups of herbivores could have huddled close together to share body heat, while during the day they could have spread out to maximize exposure to cooling breezes or shade. Carnivorous dinosaurs, such as theropods, may have employed different strategies for thermoregulation, particularly when hunting. Active predators generate considerable heat during periods of exertion, and these dinosaurs might have been more reliant on cooling behaviours after hunting. Seeking water to cool off after a chase, or finding shaded areas to rest and recover, could have been common practices. Unlike herbivores, which grazed constantly, predators like Tyrannosaurus rex or Allosaurus may have spent long periods resting after intense bursts of activity, similar to modern predators like lions and crocodiles, which exert themselves in short bursts and then rest to avoid overheating. Finally, it's possible that some dinosaurs used specific postures to regulate their body temperature. Animals today sometimes adjust their body positions to control the amount of surface area exposed to the sun or wind. Dinosaurs could have done something similar, either by spreading their limbs to increase their surface area when cooling off, or by hunching up to minimize exposure to the elements during cooler periods. Fossilized trackways provide some evidence that dinosaurs, particularly large ones, had a variety of stances and gaits, which might have helped them manage their temperature during different times of the day. Taken together, these behavioral strategies likely formed an essential part of how dinosaurs regulated their body temperature alongside their physical adaptations. Whether through careful use of their environment, group dynamics, or individual behaviors, these prehistoric creatures would have had to be remarkably attuned to their surroundings in order to survive and thrive in such diverse and sometimes harsh climates. By observing how modern animals cope with similar challenges, we can gain insight into how these ancient giants might have behaved, painting a vivid picture of their daily lives and survival strategies. When we examine the thermoregulatory strategies of giant dinosaurs, it's natural to draw comparisons to large animals living today. Despite the millions of years that separate us from the time of the dinosaurs, there are intriguing similarities between these prehistoric giants and some of the largest creatures on Earth today, such as elephants, crocodiles, whales, and large birds like ostriches. By exploring how these modern animals regulate their body temperature, we can gain valuable insights into how dinosaurs might have dealt with similar challenges. One of the most notable comparisons is between sauropods, some of the largest dinosaurs to have ever walked the Earth, and modern-day elephants. Both groups of animals share the challenge of maintaining a stable internal temperature despite their massive size. Elephants, as one of the largest terrestrial animals alive today, have evolved unique adaptations to stay cool in the intense heat of their environments. For instance, their large ears, which are filled with blood vessels, act as effective cooling radiators. By flapping their ears, elephants increase blood flow and enhance heat dissipation. This simple but effective mechanism helps prevent overheating in these enormous creatures. When considering sauropods, it's plausible that they had similar physiological adaptations. Although sauropods did not have large ears like elephants, their elongated necks and tails could have served a similar purpose. Sauropod necks were lined with a network of blood vessels, which may have helped them dissipate heat, just as elephants do with their ears. Additionally, the extensive air sac systems that ran through their vertebrae would have enhanced their ability to cool off through increased air circulation. Thus, by looking at the way elephants manage heat, we can infer that sauropods likely possessed similar cooling mechanisms suited to their unique anatomy. Crocodiles offer another valuable comparison, particularly when examining the thermoregulatory strategies of large theropod dinosaurs like Tyrannosaurus rex *. Crocodiles are ectothermic, which means they rely heavily on their environment to regulate their body temperature. However, despite being cold-blooded, they have developed sophisticated behaviours and physical features to manage heat. Crocodiles often bask in the sun to absorb warmth and then submerge themselves in water or seek shade to avoid overheating. They also regulate their body temperature by adjusting blood flow to their heads and tails, releasing heat through specialized blood vessels in these areas. Similarly, some large theropods had skulls with highly vascularized areas, which suggests they may have used their heads to release excess heat. Fossilized impressions of blood vessels in the skulls of theropods indicate a cooling function, similar to what we see in modern crocodiles. Given that theropods were active predators, they would have needed efficient ways to shed the heat generated during hunting or other strenuous activities. By comparing theropods to crocodiles, we gain a clearer understanding of how these massive carnivores might have adapted to avoid overheating despite their size and active lifestyles. In addition to comparisons with land animals, it's also worth examining how marine animals like whales manage their body temperature. Whales face the dual challenge of maintaining warmth in cold ocean waters while avoiding overheating during intense physical exertion, such as deep dives or fast swimming. One way that whales deal with these challenges is through the use of blubber, which acts as an insulating layer that conserves body heat. However, whales also possess specialized vascular structures known as countercurrent heat exchangers, which help them manage the flow of blood to different parts of their bodies, maintaining stable temperatures during dives and other activities. For giant dinosaurs, particularly those living in cooler regions or during colder periods, retaining body heat would have been equally crucial. Some paleontologists theorize that large dinosaurs like Argentinosaurus * may have had a thick layer of fatty tissue or muscle, similar to the blubber of whales, which provided insulation against the cold. Additionally, the presence of vascularized bones and specialized blood vessels in some dinosaurs suggests that they could have regulated blood flow in a way that resembles countercurrent heat exchange systems in marine animals. This would have allowed them to maintain stable internal temperatures despite external fluctuations. Large flightless birds, such as ostriches and emus, also provide interesting parallels to certain dinosaurs, particularly smaller theropods. Modern birds, which are direct descendants of theropod dinosaurs, have a range of thermoregulatory adaptations that have likely been passed down through millions of years of evolution. Ostriches, for example, are well adapted to life in hot, arid environments. They manage their body temperature through a combination of physical features and behaviors, such as reducing activity during the hottest parts of the day and utilizing their feathers to block the sun's rays while still allowing air to circulate. Ostriches also have a unique respiratory system that allows for efficient heat exchange, preventing their bodies from overheating during physical exertion. These adaptations in ostriches and other large birds hint at similar strategies that might have been used by their dinosaur ancestors. Feathers or proto-feathers found on many theropod species could have served not only for insulation but also for temperature control, helping these dinosaurs stay cool in hot weather. Additionally, the advanced respiratory systems of modern birds are believed to have evolved from similar structures in theropod dinosaurs, which would have enhanced their ability to regulate body temperature during physical activities like hunting or running. Looking beyond direct physiological comparisons, the social behaviors of modern animals also offer clues about how dinosaurs may have managed their body heat. Herding behaviors in elephants, wildebeests, and caribou, for example, not only provide protection against predators but also help in thermoregulation. Herding animals often huddle together for warmth or space themselves out to maximize cooling effects, such as shade or breezes. Fossil evidence suggests that some dinosaur species, such as Maiasaura*, also engaged in herding behaviors, with juveniles and adults moving together in groups. These social structures could have been crucial in helping younger or smaller dinosaurs regulate their body temperature by allowing them to benefit from the warmth and protection of the group. Similarly, the nesting behaviors of certain dinosaur species can be compared to those of modern reptiles and birds. Modern alligators and crocodiles are known to carefully select nesting sites that offer optimal temperature conditions for their eggs, and some bird species even manipulate their nests to maintain the right temperature range for incubation. Fossil evidence from Oviraptor* nests shows that these dinosaurs might have built mounded nests and possibly guarded or tended them, suggesting that they too understood the importance of maintaining the right temperature for their developing young. By choosing nesting sites strategically and using protective behaviors, these dinosaurs could have ensured that their eggs and hatchlings were not exposed to dangerous temperature extremes. In conclusion, by examining the strategies used by modern-day giants like elephants, crocodiles, whales, and large birds, we can piece together a plausible picture of how giant dinosaurs regulated their body temperatures. These comparisons help to fill in the gaps in our understanding of dinosaur physiology and behavior, offering insights into the remarkable adaptations that allowed them to thrive in a range of environments. From utilizing physical features like vascularized skulls and air sacs to employing complex social behaviors and environmental strategies, these ancient giants were likely more sophisticated in their thermoregulation than we might initially assume. These similarities between modern animals and dinosaurs not only highlight the continuity of evolutionary adaptations, but also underscore the ingenuity of life in finding solutions to challenges like temperature regulation. By studying living animals, paleontologists gain a valuable perspective on how extinct creatures might have behaved and adapted to their environments. This ongoing comparison between ancient and modern life forms continues to reveal fascinating insights into the biology and ecology of the world's most extraordinary creatures, the giant dinosaurs.